So if you look at this picture, then this is a shape from CERN. You can see that you've got a spacer, an RF liner with a lot of pumping holes. And this is typical that now instead of an entry and an exit, I'd like to calculate what's the conductance from the center of the pipe to the outer layer. I would typically be interested in such a question because I've got a pump attached to the outer layer. However, my gas is generating in the inside. And we will see later that it's really easy to estimate the pumping speed inside the pipe, which would be the effective pumping speed of the pump that I buy on the outside. Now, actually, I will go back to this Pfeiffer curve, because there is a formula that we will use, which is telling you that basically the gas quantity that's getting from point 1 to point B depends on the conductance and the pressure difference. Maybe, yeah, actually they are just plugging in this volume for you later, but this number here is the conductance. Which means that if I can calculate the pressure difference between 2 points in my system, and I know what's the gas quantity going through it, then I can calculate what my conductance is. So what I will do is I will inject a known gas quantity in the center of the pipe. I will pump it on the outside, and I will measure what's the pressure outside of the RF liner and inside of the RF liner. And by the difference of the two, I will be able to know what the conductance is. So I have simply opened the CAD program and generated an STL file in ASCII format. And STL is basically a triangulation of the geometry and is supported by all major CAD programs. And I did this because that's the format I can open in Molflow. Basically, the question it asked me is what were the units of the STL file. In this case, this was centimeters. In the upper right corner, we can verify that in this case we get a 15 centimeters times 22 centimeters times 15 centimeter geometry, which is more or less correct. At this point, I've got the geometry in Molflow. I can even set it to volume view, but by clicking on the collapse button, he will actually merge the triangles and it will be easy to work with. I will do one more thing, and this is once again some internal CAD editing right now. So Molflow typically assumes that your accelerator components are oriented towards the Z longitudinal axis, and this is not the case, so now it's really hard to rotate it. So I will simply select all the facets, and I will just rotate everything around the x-axis by 90 degrees. And that way it's more comfortable for me to work with this geometry. So we can see that basically, since we directly imported it from our CAD program, there are a few things that we need to do with it for a vacuum calculation. We need to plug in the holes so the molecules cannot get out at the end. We have to create a gas source in the middle of the pipe, and we have to set up pumping at the outer balls. So for this, I will use a tool which is called Smart Selection. What it does is that it analyzes your geometry and checks which facets are neighbors of each other. And that way you can easily select, for example, the inner wall with one click, as opposed to trying to draw a circle for these smart selections. This takes some time, but you only have to do it once for the geometry, and as long as you don't edit it, you can actually keep the results. Alright, and now I could click on it and he automatically selects all the walls. And by the way, you can see that the normal vectors are pointing outwards, and this is because when you import something from a CAD program, normally the normal vectors are pointing towards the solid part of the body. So actually this is a problem. I'd like to select everything, and I'd like to swap the normal, because that way the molecules will have a barrier, so you can see that they are pointing inwards and they will catch the molecules. If I'm holding the Alt, I can rotate the light direction, and then I can get back the light to a bit more natural direction. So these parts of my geometry will be pumping. I will put a sticking factor of 0.5, If I would put a too strong sticking factor, then I would barely get any statistics in this part because all the molecules would immediately leave. So let's try with a 0.5 and we will see how we do, whether this volume holds up. Remember that you only have to know your pumping speed, which in this case will be about 3,700 liters per second. We will plug it to the equation and then we will be able to calculate the conductance. Now, even if I did smart select, it's relatively difficult to select uniformly the inside of the facet. So you can see that some facets are missing. So I could either set it as a gas source, the inner wall, or I could even create like a shape in the middle that will be desorbing gas, and I like the solution better. So what I will do, I turn off Smart Select, and I like to see the coordinates of my geometry. So I will be plugging in my geometry at the both sides, and here I select two vertices. For this I'm pressing the Tab key, and I will just check their coordinates. So I can see that one is at like, so the 0 point is here, so one is at minus 0.2, the other is at minus 17. So I will simply create 4 vertices. One will be at, let's say, minus 15, which is safely inside the tube, or right here. Then I put minus 1, then I will put number 3, and finally number 4, and then I can select a facet out of this. There are many ways to select, to create outgassing inside the volume. One of them would be to use the create shape, and then I simply orient it upwards, but this was the easiest for me at this point. And at this point, since I'm already with coordinates, I will also create a new facet, which I will use to sample the pressure inside and outside. So for that thing, I will keep this coordinate. I will go to the center line, and I will create a vertex up. Maybe it's too much. I will just, let's try 7. Yeah, 7 is fine. I will put minus 7. Then finally I will put minus 15 and plus 7. Alright, and I will just create one more shape. So this shape, I will use it to count the pressure inside and outside my system. So I will make it transparent, I will make it two-sided so you can catch hits from both sides. And I will add the texture, which will count all the transparent passes. And by trial and error, I put 10 here, and this would result in 1900, 600 cells. So actually, this is good for me. I have created a texture on it. And now thinking twice, maybe it would be better to actually make this go through the whole body. So I will just move this vertex a little bit downwards, and that way I increase the sampling to my whole geometry, and I will just ask Molflow to remesh the surface, so now I got a texture. Remember that earlier we have created this shape in the middle, which is creating the outgassing. I will just select it. I will create a desorption. I will make it two-sided. Alright, and finally, the thing that I have to do is to plug the holes at both sides. So to plug the hole, I will go to vertex selection mode, and here I will select 3 vertices on the outer line of the hole that I'd like to plug. At this point, it's a good idea to rotate the geometry and make sure you have selected everything correctly, as opposed to, for example, somewhere else in the body. So I will just deselect this. And there is a command, it's called select coplanar vertex, which will automatically select everything in the plane. So now he has selected the whole, but also some other parts. So I will simply clean up the selection to restrict it to only the whole. Alright. right, and at this point I can actually create a new facet which will be a plug. I just need to turn it to face the inside, and that way it will be plugging in my geometry. Here on the other side, it's a little bit more difficult because actually the RF cavity is ending a little bit before the edge of the geometry, so particles could escape it. So what I will do is I will create a plug a little bit at the inner side. For example, I could use this line here, which already exists in my geometry. So I could say select these three vertices, they are on the same plane. I could ask to select all the coplanar vertices, clean up my selection, create a plug, and so on and so on. However, at many times you have to create a plug on your own, so this is what I will be doing. Simply I will create a new shape. So it will be a circle. Let's have it 100 sides, it doesn't really matter. It has to be larger than my geometry, so for that I will just check the dimensions of, here I can select a circle. In the details I can see that it's about 15 centimeters times 15 centimeters. So by putting, let's say, 17 centimeters, my plug will be larger than the whole geometry. And then I'd like its normal vector to face to the minus z direction, otherwise the coordinates at 0, 0, 0 are correct. So I've created my plug, and to make sure that I plug the whole geometry, I will just move it down a little bit in the inside. So basically I'm gently placing it here, so that way it crosses my geometry. At this point it's maybe a good idea to save the simulation, so I will just put test rf.zip as the file name, and I can launch my simulation. So I can see that my particles are flying in the system. I have no leaks. I can actually put a little bit more lines on the systems. And most importantly, even if the visualization is not the best, I can see that here I've got some gas source as expected. Then I've got like a much lower pressure on the outside and a higher pressure in the inside. So in this case, what I would need to do is actually get the average pressure on the inside and get the average pressure on the outside. One way to do that would be to actually use the values. Here on this vertex, I can go to texture plotter, and by putting it on full screen, I can see the map of my system expressed in texture cells. So one easy way to post-process it is I will just paste this into Excel. Okay, I will just apply conditional formatting so I can see the color scale. I will zoom out a little bit. This is essentially what we're seeing in Molflow. So here you've got your pressure profile. And by selecting a large area, Excel is telling me that my average pressure inside is like 9 to the minus 4 millibars. Remember that we chose some arbitrary quantities. 9 to the minus 4. And inside 2 to the minus 4. So basically, by plugging into this formula, the pressure difference, so I know that the left side of the equation is actually 1, because our outgassing rate was 1 millibar times liter per second, and I have to divide it by this 0.000, I think it was, yeah, let's check the pressure again. It was something like, yeah, 9 to the minus 4. And the pressure difference was actually this. And that times I get a conductance of 1428 liters per second inside to the outside. This tutorial, I'd like to show simply like 2 things that can make your life easier. One is that if you go to Smart Selection, then you can select all the faucets that are on the inside, so those that are pumping. And if you go to Details, then you can query the pressure on the inside. You can see that more or less you still got this 2 to the minus 4, but there is some statistical scattering. You could obviously once again just copy the column, go back to Excel and calculate the average, which is like 2.2 to the minus 4. But even within Molflow you can do that. You actually go to Formula Editor and you can write a formula which is basically averaging physical quantity over the selection. So in this case you would ask the average of the pressure on the selected faucets, which is now 2 to the minus 4, and that way you can even like select the inside. Yeah, I will just try to close a few windows so I can see better, and if I click correctly then I can select the inside of my system. This is the outside and this will be the inside here. And that way, if I recalculate it, now I get a slightly higher volume. It's like 1.1 to the minus 3 as opposed to 9 to the minus 4. You can see that since my outgassing is not uniform, actually there is a small pressure gradient. Depending on where your gas is coming from, maybe it would have been a better idea to actually, instead of a small desorption, I should have put it for the whole system, and then I wouldn't have these pressure differences. And finally, it's always great to check if our calculations stand up to basic physics equations. So, so far I have used, so basically I divided the total outgassing by the pressure difference, and you might remark that if we in the beginning we have set a sticking factor of 0.5, which corresponds to about 3.7 thousand liter per second. Don't forget that this is a large area, so the high pumping speed is actually warranted. And let's check if we still get the same result if we change the pumping speed. If conductance is indeed only depending on the geometry, we should get exactly the same volume, so it's worth playing with it a little bit. So let's go back to our calculations. Since our pumping is lower, now the pressure difference is much lower between the inside and the outside, and that's why we would need to run a longer calculation, typically for, let's say, 20 minutes, depending on your computer. And then once again I will just select the inner body, so I will go to Smart Select. These are my sticking faucets. I can see the pressure on them, that it's about something like 1.3 to the minus 3 millibars. Remember that these are like arbitrary units, since my outgassing was 1. And go back to the formula editor. Now I can see that actually the outer pressure has pretty nicely converged. So I got 1.3 to the minus 3. And for the inner pressure, just to be able to calculate with the previous method, instead of Smart Selection, I will once again export the texture, and I will take an average in the volume. So I go to Texture Plotter, copy everything, go to an Excel sheet. I will just go to the upper left corner and paste this. And here I can see my pressure distribution, so you can see that clearly there is like an outer layer with lower pressure and an inner layer. To calculate the inside pressure, I will just draw an area more or less in the middle. And here I can see that the average is like 2.2 to the minus 3. So in this case, I will take 2.2, and from that take the 1.3, and now the pressure difference is slightly larger, so I get a little bit different conductance, but probably as the calculation would converge, I would arrive to the same values. So remember that here the statistical scattering is still relatively high, and depending on which area I take, the values might differ. But still, I have radically changed the pumping speed to 1/5, and I got more or less the same conductance, obviously with plus minus 10% scattering. So this is how you would actually calculate real-life geometry, which is more complicated than just a long pipe. So this would be like a real-life unit. Simulation run a little bit, and now you can see that the texture is much more smooth. So this took about 10 minutes of calculations on a desktop computer. And actually running the simulation a little bit longer also reveals what's going on. So you can see that the pressure is not actually symmetric. There is a high pressure bump here. You can see what the colors mean if you go to the texture scaling window. So you can see that the purple is actually meaning high pressure. And by the way, this could be also a good estimation that if you take your cursor here, then on the left you can see that it's about 2.2 to the minus 3, representing the blue color. So in the volume mode, I can see inside a little bit, and you can see that actually the problem is that the desorption is coming only at one side, and the area of pumping slots are ending here. So basically here on the left, the volume, the gas particles need to find their way to the first pumping slot, and that's why the pressure is locally higher. So there is a pressure gradient, and depending on where I take my pressure sample from, I might get different values. So that's why this is one more reason why I should have either plugged the system here and here, so I got a continuous system, or I should have created the desorption all along the center axis. Still, I hope that this tutorial was useful for calculating conductance of a really difficult CAD structure. So once again, we can see that this was the original structure. We didn't do any simplification, but only plugged in the sides and the ends. We created some desorption from the center, and we created pumping on the outside, and relatively quickly we could calculate the conductance.